Good
Should I
evening.
share
I
the screen?
welcome you all to the 35th session of the CENTA webinar series for teachers. Those of you who've been regular attendees of our webinar series would remember that sometime back in August, we had done a session on the relevance of Sanskrit texts to contemporary math syllabus. Those of you who attended the session had loved it, and you'd requested us to do another session on similar lines. So here we are. We are back with a similar session, and we're back with the very same facilitator, Mr. Sripathi Sripada. Welcome back, Sripathi.
Hi, thank you, Karthik.
As you already know, Sripathi is currently the VP of Platforms and Digital Branch of the Banking, Financial Services and Insurance vertical at Tech-Mahindra. He graduated in chemical engineering from Andhra University, did his MBA from IIM Calcutta, and is passionate about mathematics, Sanskrit, grammar, yoga, philosophy, and of course, teaching. Great to have you with us again, Sripathi, and all of us are looking forward to another fantastic session. And just before you start, a quick announcement. Hi, teachers. This is on the the feedback form for getting the acknowledgement record. So we're going to be following the same drill. The feedback form is going to be available here in the live chat section from 5:45 onwards, and it's also going to be available on my center home screen itself, the same place that you used to register for the session with Sripathi, exactly the same place. You just need to click on it, and the feedback form is going to open up. You need to fill that up, and the acknowledgement record is going to be sent to you via email by noon tomorrow. So please make sure that you do that by 9 p.m. today, so that the certificates can automatically, the acknowledgement records can automatically reach you, and you don't have to follow up with us on email. Having said that, that's pretty much it from me, Sripati, for this introductory part. So I'm just going to take leave, and over to you.
Thank you, Karthik. Firstly, a big thanks to Karthik and the CENTA team for organizing this. We did a session, as Karthik said, in August, and some of you, I'm sure, were a part of that session. However, a quick introduction. While I'm work in IT, I'm very passionate about Sanskrit and mathematics written in Sanskrit of Indian texts, and this is a sort of a small initiative to share whatever I've learned over the years, in as my hobby. It's a hobby. Well, I'm not an academician, but I love teaching, and nothing better than teaching, an opportunity to share learnings in Sanskrit and in mathematics. So welcome everybody. So what we did last time, we did an introduction to Indian mathematics, and I also introduced a few techniques. We will build upon that. Not to say that last time session was mandatory. It's nothing like that. These are all simple concepts, and all of us will be able to follow them. And we all, just a quick reminder that we all know the relevance of mathematics that was developed in India. The concept of zero, of showing zero in the number system when a particular place value does not, a place value does not have a digit, it is represented by zero. That concept originated in India, and one of the first people to use that concept in notation of number systems was Aryabhatta, way back in around 400 AD. Now, the concept of writing numbers from right to left and increasing place values from right to left existed before that. And there are old statements in Sanskrit like Ankanam Vamato Mukha. You read numbers from right to left, basically meaning the place value system increases from right to left. So this system was in existence for a long time in India. Maybe somewhere around the oldest records you will find, minus maybe 300, 400 BC, you will find number systems written from right to left. And that was given a formal shape by people like Aryabhatta, Brahmagupta, etc. later on. And it's fundamental to any advancement in science. If you can't count, if you can't count with a notational system that allows you to do all the arithmetic operations, there is no progress in science that is possible. A quick list of some of the important texts written in Sanskrit regarding mathematics. There are texts from the Vedic period. You will find in the Vedas here and there, which talk about calculations and arithmetic, etc. And there are formal texts that are written in what can be called as the classical period. There are a number of texts. You will find at least a good 2-3 dozen texts if you go back and do some research. But some of them are seminal in terms of the what they addressed in the areas they addressed in mathematics. And so that's the source and inspiration for some of the work I'm sharing today. And there is also a question: is the mathematics that was developed in India not subsumed by modern mathematical development? Of course, the answer is you can't say no, it has not been subsumed, because mathematics as a subject has evolved significantly in the last millennia, and a lot of these concepts have sort of evolved. So it's not the work is not about saying that no, it was done in India only, and this is how it was done. But the idea is to take inspiration from the scientific rigor the Shastrakaras had when they wrote any Shastra. So there was a amazing amount of scientific rigor, and that sort of gives a nice, and that is where the relevance comes from, and the way they looked at scientific topics and the rigor they had in writing those documents. Very quickly, again, any Shastra you would find these four. If you go back to old Indian Sanskrit-based texts of any science and look at them, they will start with what is called Anubandha Chatushtayam, which is a relationship between the objective of the study, the objects of study, and the adhikari, or the person who is qualified to study that subject. That's called Anubandha Chatushtayam. If you go open any Shastra book, the first 2 or 3 shlokas in the Shastra book will lay down what is the objective of the study. So that sort of, and the entire document then sort of relates to the objectives laid out in the first or second shloka usually. Yeah, and this rigor, when it comes to mathematics, now mathematics texts were written with multiple objectives. The basic one being what is called Vyakta Ganita or Pita Ganita, which is arithmetic, right? Arithmetic in terms of, and lot of the mathematicians treated the 8 operations which we use today as the basic operations. And in one textbook of Brahmagupta, you will find 20 operations. So he sort of added, summation of series and ratio proportions, all of that qualified into what he termed as basic arithmetic operations. Then there were texts written with the objective of algebra or bija ganita or avyakta ganita. Then there is geometry, mensuration, trigonometry, and advanced astronomical calculations. And what they did was they used to then summarize their teaching into what is called sutras. Now, this is a very important thing to understand as to what a sutra is and how they would write sutras. And I would also show you as we go through a few techniques today to how we can write these sutras ourselves. The basic definition of a sutra is it's Swalpaksharam, Asangdigdham, Saravat, Vishvato Mukham, Astobam, Anavadyam cha, Sutram, Sutra Vido Viduhu. The one who knows a sutra will tell you these are the characteristics of the sutra. There are 6 characteristics of a sutra. And a very rough translation of sutra, you can say a generalization or a formula. It's not exactly a formula, but very rough translation in English can be a formula. Now, it has to be Swalpaksharam with these minimal syllables, because knowledge was primarily transferred orally than writing down. Even today, you might notice with your students, and I do notice this with children I teach as well once in a while, that whatever is transmitted orally gets transmitted without any errors. But in a written textbook, there are chances of confusion and and not able to understand what is written in the textbook. But whatever is conveyed orally, humans understand very well. And if you make a habit, whatever is transmitted orally, people can also remember very well in the order of in which it was transmitted. So the error of the probability of error in oral transmission is very, very, very low. But the probability of error in confusion in written transmission becomes very high. As people write, they can make errors, all of that. So it was always, a sutra always had minimal syllables on. Then it need to be without any confusion. That's asandigdam. Saravat, it should be in summary form. Whatever you want to say, you should be able to say in very minimum number of syllables. Vishvato Mukham, universally applicable. Now I give a formula for addition, then I should be able to use it for addition across wherever numbers, arithmetic, wherever I see addition, I should be able to use it. So that should be the type of conception of a sutra. Astobham without any errors, and anavadhyam without any redundancy, because you want to transmit orally. It should not be, you should not be repeating saying unnecessary words in the sutra. So this method was used right across, not just for mathematics. And one of the prime examples, this slide is a short digression from maths, but one of the most interesting examples and very well acknowledged examples is Sanskrit grammar sutras of Panini called Ashtadhyayi. If you look up Encyclopedia Britannica and search for Panini's Ashtadhyayi, it says that is the closest example of a Turing's computer, the Ashtadhyayi set of sutras. There are 4,000 sutras, and with 4,000 sutras, Panini, somewhere 3,000 years ago, created a grammar, which is constructional grammar. So if you know those 4,000 rules, you can create new words, new expressions in Sanskrit, and not only that, you can, if somebody else creates a new word, you will be able to understand it. So Panini's Ashtadhyayi is a mathematician's delight. It is called the perfect example of a Turing's computer. So just to say that the sutras have been used in a very, very powerful manner by the acharyas of the past, and they created sutras for maths, for grammar, for logic and reasoning, for physics, for the psychology of the mind, which is called Yoga Sutras, for also philosophy of life, which is called Brahma Sutra. So it was not just in maths, but very widely used technique by all the acharyas across fields of science. Now that's to me, that's a beautiful inspiration to take and see, can we create our own sutras in the subjects, whatever subject we are teaching, whether it is mathematics or physics, or even arts, any subject we teach. Can we encourage students to understand the concept and then condense it into a small phrase or a sentence, which can be called a sutra, which has those 6 characteristics which we talked about. So in the last session, we did 4 basic operations, and we sort of created a set of sutras in English, which look like this. Now what we will do is we'll take a couple of these and expand them a little bit and show how these sutras are very powerful if you are able to condense the subject into a generic statement, which can be utilized later on wherever you come across such a situation. Now text would be written in sutras like this, and then there would be commentators who would then write thousands of pages on commentaries on a small book of 50 pages. You can write a few thousand pages of commentary by explaining, but that small book of 50 pages can be easily transmitted, remembered by students, and then they can use it to go through it again and again and understand it in different ways, etc. So what we'll do today is we'll take up multiplication and see how we can apply the same sutra from decimal system to other number systems to algebra. And second thing we will take up is division by 9, or in algebra division by x minus 1, division of f of x by x minus 1. So we'll take these 2 areas and see if we can build a consistent set of phrases which we can call sutras. So first, the technique. So I will be writing, I'll be solving the problems as I speak. So if anybody has a doubt, Karthik, please feel free to stop me and ask those questions. So first one is a simple multiplication of a 2-digit by 2-digit number. We saw this last time as well. So if I am multiplying 2 2-digit numbers, which means there are 4 digits, the answer will have 3 parts. Now there is a logic here, right? Because 2 digits mean there is a tens place here and there is a tens place here. If you multiply tens place and tens place, you'll get a hundreds place, and then hundreds place, tens place, and units place. So you're basically evaluating the multiplication place value by place value, and the pattern is as shown here. It's a very obvious, once you are addressing it place value wise, it's an obvious pattern. So the hundreds place value comes by multiplying the 2 tens place digits, that is 2 into 3 6. Then the tens place value will come by multiplying tens into units and tens into units. So in this case, it will be 2 into 2 plus 3 into 4. That's 4 plus 12, 16. And then the units place will be unit into unit. So that's 4 into 2, 8. Now we also know each place value can have only one digit. So this moves to the left. So this becomes and gets added to 6, 768. So that's a very simple way to represent a 2-digit by 2-digit multiplication. It's a pretty obvious method. Once you know once, it's very, very easy to do this calculation. And you can do the calculation left to right as well with a little bit of practice. Then if we take a larger number, slightly larger number, 3-digit by 3-digit, now the pattern expands. With the logic is the same, that because I'm multiplying two 3-digit numbers, that is units, tens, hundreds. Hundreds into hundreds will give me a 10,000s place, and then reducing place values from 10,000s on the left side. So the 10,000s place will come by multiplying the leftmost. So that's 4 2s are 8. Then the thousands place will come by 100 into 10. So hundreds digit into tens digit. There are two combinations, so you multiply them. So 4 6 24 plus 4 30. Sorry, 28. Then we have the hundreds place. Hundreds place will be hundreds into units. So there are 2 hundreds into units and 1 10 into 10. So that's 20, 22, and 12. That's 34. And then the tens place, it's 10 into units, 10 and 6, 16. And then the last one is 5. And then you pass the extra digits. So 5, 6 comes to answer. This 1 will travel here. So that becomes a 5. This 3 will travel here. So this becomes a 31. 1 goes to the answer and the 3 travels left. So that's the product of the multiplication.
Sripathi, sorry to interrupt, but a couple of teachers, Miss Sia and Miss Nalini, have a doubt and they are requesting if you could repeat this again. So
Yeah,
would
I
be
will.
really helpful. Yeah.
I will.
Thank you.
So when you are multiplying 2 3-digit numbers, so the answer will have 5 parts as I've drawn there. 5 parts means why 5 parts? Because I'm multiplying 2 3-digit numbers that have a units, tens, and hundreds, right? So when I'm multiplying 100 into 100, I'll get a 10,000s place. So the 5 parts means this is 10,000. This is thousands part. This is the hundreds part. This is the tens part. This is the units part. Okay. Now 10,000s will come by multiplying the hundreds place value digit into hundreds place digits. That's 4 into 2, 8. That's the pattern. Then the thousands will come by a crisscross, which is 4 into 6 and 2 into 2. That's what is the pattern, shows. That's the way to draw the pattern so that we remember. Then the hundreds place, you can get it in 3 ways. That is hundreds into units. There are two combinations, 4 into 5 and 2 into 1. And then there is a 10 into 10. That's the pattern here. So that's 34. And then the tens place is 2 into 5 plus 6 into 1. That is 16. And the units is 5 into 1, 5. Now, once you get the place values, that is 8, 28, 34, 16, and 5. Now, we know in the number system, each place value can have only one digit. So what happens is the rightmost digit goes, the leftmost digit goes left each time. So 5 comes to the answer, 6 comes to the answer, 1 goes left, 34 plus 1 becomes 35, 5 comes here, 3 travels here. Then 28 plus 3 becomes 31. So out of 31, you take 1 to the answer. And this 3 travels left, gets added to it, it becomes 11. So that's the way to multiply. It's definitely easier than traditional multiplication. If with a little bit of practice, what we could also do is we can avoid drawing the pattern. Once we know it's the pattern, I can start from left to right. I know 4 2s are 8. I know the next part is 28, so I'll write 2 and 8 here. I know the next part will be 34, so 3 and 4. The next part is 16, so 1 and 6. The next part is 5. So I'm basically passing as I go from left to right. Then I add 4, 6, 5, 11, 11. So very neat. It's a very neat way to do multiplication, to practice multiplication, and children actually find it very useful once they do a few few multiplications in this manner. Now the same we can extend to bigger numbers. The logic is the same. So if you are multiplying, 4-digit by 4-digit, it's not 4-digit by 2-digit. If you are multiplying 4-digit and 4-digit, so you'll have 7 parts, and the 7 parts will be as shown by the pattern here. So, and I can go from left to right or right to left, whichever is comfortable. I mean, I'm doing left to right because just to show that multiplication can be done left to right to a large extent. So I start left, the leftmost, 2 into 4, 8 here again. Then I have 2 into 0 plus 4 into 1. So that's 4. Then I have 2 5s 10 plus 16 26 plus 0. So that's 26. Then I get 2 plus 12 14 plus 5 19. Then I get 1 plus 20 21. Then I get 4 plus 15 19 again. And I have 3. You can pass. So you'll get 3 9 2. This one will go here. This one will go, this 2 goes here and this becomes 21. So I get 1, 2 travels here. So I get 8. This 2 goes here, 8 and 6. So that's the product of those 2 numbers. So it's actually a very neat way to do in rough work for children as well. It is so that's how we multiply 2 4-digit numbers. Now the pattern, once children know this pattern, they themselves will be able to then multiply bigger numbers, 5-digit by 5-digit, 6-digit by 6-digit. You can take the same, children can also try out writing a computer program using this to multiply numbers and match it with computer's time. It does faster than computer's own multiplication time. If children are, 9th standard, 10th standard students are interested, 8th standard students, they can quickly write a computer program for this and check with, whether this is faster or computer's normal routine of multiplication is faster. This beats the computer for the larger the digit, the faster this is.
Sripathi, Narasimha ma'am has a question, and she's saying, okay, we're just gonna get to that. She's saying if it is 3 digits multiplied by 4 digits, as in the digits are not equal, how do we go about that? That's exactly what you're coming from. Yeah.
Yes, exactly. So this is now the same logic. The logic is the same, right? So if I am multiplying 3 digits and 2 digits, which means I have units, tens, hundreds in the first digit, and then units and tens here, which means the leftmost will be 100 into 10. That's a thousands place. So thousands, hundreds, tens, units, which means I'll have 4 parts. Or the easy way to remember is total number of digits in the multiplication minus 1 is the number of parts. So I have 5 digits, 1, 2, 3, 4, 5, minus 1 is 4 parts. So now you can I start from right or left again. I'll do once from right to left and then I'll show from left to right as well. So start with the rightmost, which is 3 into 1. That's simple. 3 into 1 is 3. Then 4 into 1 plus 5 into 3. So that is 15 plus 4, 19. Now what happens is the multiplier moves 1 step to the left. And then you apply the same pattern. 2 into 1, 2 plus 5 into 4, 20. That is 22. And then finish off with 2 into 5, 10. And then you pass the digits. It is 3, 9, 3, 12. That's the product of 243 into 51. We just have to remember that after finishing the pattern, the multiplier moves 1 step to the left and it will keep moving. If there are more number of digits, it will keep jumping 1 step at a time until you reach the leftmost. And the way to check the pattern is just go by the logic that units place value has to come from unit into unit. Tens place will come from 10 into unit and 10 into unit. Hundreds place will come from 100 into unit and 10 into 10 in this case. And the thousands place will come from 100 into 10 in this place. That's what is happening as the multiplier moves. You can also do the same from left to right. So starting with the multiplier moved first, then I write 10, 2 5s are 10, then I have 22. Yeah, and then this is done. The multiplier moves back to its place. Then I have 4 plus 15, 19, and then I have 3. So I get 1, 2, 3, 9, 3. So that's how you can multiply when there are unequal number of digits in the two numbers. These patterns are easy to build. I mean, once you teach a few patterns and just leave the kids to build their own patterns for bigger digits, they'll be able to do it themselves. One more, just to show that this can be extended. So that's the pattern. So 52 will start from the left first. So I do 52. So 2 5s are 10. Then it is 24. And then this is done. It will move one step to the left. So this becomes 8 plus 15, 23. Then this is done. It will go back to the rightmost place. So 6 plus 5, 11 and 2. If you pass the digits, you will get 1, 2, 6, 4, 1, 2. So that's the method. Now the beauty of this is it doesn't just stop here. You can then extend it to algebraic multiplication. The same patterns work for algebraic multiplication. In fact, if you now look at the pattern will be very apparent, because that's exactly what we do when we multiply algebraic expressions. If I just told you algebraic expressions first and then said let's apply this to numbers, then the pattern is much more obvious here. So you have, for example, if you are multiplying 2x square plus 4x plus 3 into 4x square minus 3x plus 1. So I just write the coefficients 2, 4, 3. 4 minus 3. Minus 3 I just used bar 3 so that I don't confuse it with the operations. Bar 3, when I write bar 3 means it is minus 3. Minus bar 3 and then 1. So, and now I do the same thing. 2 4s are 8. Minus 6 plus 16 is 10. Then I have 2 plus 12, 14 minus 12, that is 2. And then I have 4 minus 9, that is minus 5. And then I have 3. Now here, there is no passing the digits in algebraic multiplication. We just write the coefficients of x starting from the rightmost. This is the constant term, then x square, x cube, x power 4. So the answer is 8x power 4 plus 10x cube plus 2x square minus 5x plus 3. That's the way to multiply.
Sripathi, Sachna ma'am has a question on this, and she's asking, is it helpful to get the coefficients of the terms and product in this method?
Yeah, so you're directly getting the coefficients, right? You can do the process either with just the coefficients, or you can also write x square, x, etc. if you want. So it's directly giving us the coefficients of the multiplication. So if there is a question, what is the coefficient of x cube in that product, I don't have to do all the multiplication. I know I just have to do these two. So by understanding the pattern, we will know immediately. We will be able to say what is the coefficient of a particular term in the product.
Sure.
Similarly, we can use the moving multiplier technique to do algebraic expressions of unequal number of terms. So 4 minus 3, 5, and I have 3 minus 2. So I start with 3 and minus 2 here. And I go 12, minus 8, minus 9, minus 17. Yeah. And then I have, this is done. So 6 plus 15. 6 plus 15 is 21. And then this is minus 10. So it will be 12. So this is x square, x cube. So 12x cube minus 17x square plus 21x minus 10. So you can then extend it to any kind of algebraic expressions. The same pattern. So what is happening here is when we can actually teach children that algebraic multiplication and numerical multiplication are no different. I mean, we typically learn them as at two different points in the education in different classes. But essentially, what is happening, what we are able to then tell them is that it is these two are not different at all. Just that in numerical multiplication, x becomes 10, and then you will then pass those digits. But otherwise, the process for multiplication is exactly the same, and hence the process is consistently being applied across numbers and algebra. Not only numbers and decimal number system, but you can also extend this to other number systems. So, for example, if I were to do this multiplication in quinary, 232 base 5 and 41 base 5, I will use the same process. But only one thing I need to know is in quinary system, 2 into 3, 6 is not 6, it's 1, 1. Quinary system is if I have only digits 1, 2, 3, and 4. I'm using only these 5 digits to build numbers like binary system, right? So if I was doing, I can then consistently apply here as well, as long as I know multiplication tables in quinary system. So 2 into 3 in quinary system is 11. Similarly, 2 into 4 in quinary system is 1, 3. 3 into 3 in quinary system is 1, 4. 3 into 4 in quinary system will be 2, 2. This is what I should know to be able to apply this consistently. Now then I can go, start multiplying 2 into 4. 2 into 4 is 1, 3. So the leftmost past is 1, 3. Then 2 into 1 is 2. And 4 into 3 is 2, 2. So this is 2, 4 in quinary system. So at each stage, I'm actually doing the arithmetic in the quinary system itself, if you notice. So then this 4, 1 is done, it goes back. So 3 1s are 3. And 4 2s are 8. 8 is 1, 3. Now I should also know 3 plus 3 is 6 is 1, 1, not 6 in quinary system. So this is 1, 1. So it is 2, 1. And then 2 1s are 2. Then I pass 2, 1. This 2 is going here. So this will become 3, 1 in quinary system, 1. And this 3 goes here. This will become 2, 1. 2, 1. So base 5. So what we were able to do is use the same process consistently across all number systems and algebra. That is the beauty of these sutras, or the technique. Now this technique is taken from Vedic maths book, but the insight is that process can be consistently applied across number systems. I can do multiplication in hexadecimal system, or binary system, or algebra, all in the same consistent method. There is no, we are not learning different methods for different different number systems and algebra. That is what I personally like in this technique. Even though the technique looks very simple, but the application is huge in terms of how you can extend it to algebra, and then you can create your own abstract number system using algebra and define a multiplication between those number systems in a very abstract manner, consistently with the same two-liner we saw at the beginning. Yeah, and the same we can extend to squares. Squares is nothing but a special case of multiplication. So if you do 4 3 into 4 3, so the first part will be 16. The then part will be 4 3 is 12 into 2 24, and then it will be 9. So it is 1849. Similarly, I can then extend this to 2 3 base 5 into quinary, squaring quinary numbers. So this is 4. Then I have 6. this 12, right? 12 in base 5 will be 2, 2. Then I have 9. 9 in base 5 is 1, 4. So that becomes 4, 2, 3, 4. Sorry, this is not the 4, 3, 4 plus 6 is 4 plus 2, 6. Yeah. Yeah. 1, 1, 3, 4 in base 5. So this is how we can take one technique and show the same technique, how it repeats itself in a variety of places we see with multiplication. Now I won't go into this. So it's again squaring of algebraic expressions. You can use the same pattern and the same method to do squaring of algebraic expressions. And all we have to remember is these two lines. You evaluate place value wise, and the pattern is vertical and crisscross alternating. So if it's even number of digits, it will only be crisscross. If it's odd number of digits, there will be a vertical stick in between. So that's all we need to remember in the pattern. Now, once we know there are a few patterns, this is all we need to know to multiply any two given numbers or any two algebraic expressions. And then you can neatly encourage children to write their own set of sutras saying, okay, let me define a number system of x digits from 0 to x minus 1 for all integers greater than x, greater than 1. That's a number system. If x is not an integer, then it's an algebraic expression. And to multiply two quantities, whether it are two digits in two numbers in a number system x, whatever the name of the number system is, or two algebraic expressions, all we have to do is evaluate place values and vertically and crisscross. And if we are multiplying numbers, then pass extra digits to the left. That's a small routine or a set of a small sutra. Children can write their own sutras in their own words, just to basically concising the the concept is concised into a few words or phrases. This is one. The second example I thought I'll take is remainder of division by 9. Now, we define something called digital root. It also called digit sum in number theory. Digit sum, or S of n, it is sometimes represented as S of n. It is a digit sum of all the digits until we get a single digit number. So we repeat the digit sum until we get a single digit number. And what we get at the end, the single digit number, we can call it a digit sum or a digital root. We call it the digital root. And the digital root is always the remainder of division by 9. Okay. So for example, if you take 623 and I have to find remainder of division by 9, all I have to do is simply add the digits. 6 plus 2 plus 3 gives me 11. And it's a 2-digit number, so I add it once again, I get 2. So 2 is the remainder of division by 9. Doesn't matter how many digits I have. If I take a bigger number, I just add them until I land up at a single digit number. This is what is this is what is mentioned in when children start studying number theory. They introduce this concept of digit sum, S of n. But what is not told normally is that you can arrive at the same thing by cancelling out all the 9s in the number. So for example, if I have 6, 2, 3, 6 and 3 add to 9, I cancel them out. What is left is 2. That is the digital root or the remainder of division by 9. Similarly, for 4, 5, 8, 2, 4 and 5 I cancel out. What is left is 8 and 2. Now I add them, I get 10. 10 becomes 1 plus 0, 1. So the remainder of division by 9 of that is 1. So you can easily arrive at the remainder of division by 9 by cancelling out all the 9s in the number and adding the remaining digits until you get a single digit number. Now the proof is also very, if you think a little bit, it's a little obvious. It's not so difficult to understand why it works. So this is 600 plus 20 plus 3. Now when divided by 9, 600 leaves a remainder of 6. 20 leaves a remainder of 2. 3 leaves the remainder of 3. So you add them to get the final remainder. 11. Since 11 is greater than 9, you divide it once again, you get 2 as the remainder. So the proof is also, it's not very difficult to think through. With a little bit of thinking, you see why it is, why the digit sum gives the remainder of division by 9. Because 100 when you divide by 9, remainder is 1. 600 when you divide it is 6. So it's not a difficult thing to prove algebraically as well. And then the same thing can then be applied to other number systems. So in a decimal system, we had digits 0, 1, 2, 9 in decimal system. This is decimal system which we use. Then if I go to quinary, I have 0, 1, 2, 3, and 4. So if after 4 I get 1, 0 and 1, 1, etc. So what is equal to division by 9 in decimal system is nothing but division by 4 in quinary system. So whatever is applicable to division by 9 in decimal system should be applicable to division by 4 in the quinary system. So I need to find the digit sum in quinary for 423 for 423 to find the remainder of division by 4 in quinary system. So if I start adding, and I can say one way is add 4 plus 2 plus 3. That's 8 plus 3, 11. 11 in quinary is 2, 1. And you add again, it is 3. Did I miss something? 4, sorry. Something. It's 11. So 11 in quinary will be, so 4 plus 2 is 1, 1, 1, 4. Sorry, it's 9, it's not 11. Sorry, 1, 4. 1, 4, if I add again, I get 5. 5, it's not 5, it is 1, 0. And 1, 0, when I add again, I get 1. So 1 is the remainder of division by 4 in, of 4 to 3 by 4 in quinary system. Or the easier way is, in decimal system, we were cancelling out 9s. Here we cancel out 4s. If I cancel out 4s, I'm left with 2 plus 3. 2 plus 3 is 5 in decimal, but in quinary 2 plus 3 will be 1, 0. And 1 plus 0 will be 1. And that's how I get the digital root of 1 for this in quinary system, and the remainder of division by 4 in quinary system of this number is 1. So you can extend, as you see, like we did with multiplication, here also we can extend the same process to find remainders of division by 9. Or in general, if I have a number system of x digits, I am dividing by x minus 1. So this is the remainder of division by x minus 1 of a number in a number system of x digits. So it's consistent with the logic, and you will be able to logically think through why it works in all number systems. Hexadecimal system, for example, is 16 digits. 4C3. 4C3. So here you cancel out 15. 4 and C make 15 in hexadecimal. So all you left is 3. So the remainder is 3 in hexadecimal system. Sorry, it's not 5, it is 16. Yeah. In hexadecimal system, the remainder of 4C3 by 15 is 3. So you can consistently apply the same process across number systems. And there are very, very interesting applications of this digit sum in number theory. So if you have big numbers like this, let's say I form a number I just took a sample problem from some number theory exercise somewhere. So if you have a number like this formed by writing all the digits 1, 2, 3, 4, 5 all the way to 1002, and if you have to find the remainder of division by 9. 1, 2, 3, this is the number 6, 7, 8, 9, 10, 11, etc. all the way to 999, 1000, 1001, and 1002. Now we know this number is divisible by 9 because 9 cancels out, 1 and 8 cancel out, 2, 7 cancel out, 3, 6 cancel out, 4, 6 cancel. which means I can then extend the same logic that all the way till 999, everything we cancel out by cancelling out nines. All I am left with is these three, this portion. So if I add the digits 1, 2, 3, 4, 6. So 6 is the remainder of division of this big number by 9. So this digit sum rule and the cancelling out 9 has very, very interesting application in number theory problem. You can solve a very nice, very lot of problems you can solve in a very interesting way. Now it doesn't stop here, the application. You can take it to...
Sripati, just a question. Sachinamam is asking if this is applicable to irrational numbers as well.
No, this is numbers only.
Sure.
Irrational numbers, we can devise a different rule, but not this one.
Sure.
Because we are talking of remainder of division by 9. So now you can extend the same to remainder of division of an algebraic expression by x minus 1. Yeah. So for example, if I had 423 in my decimal number system, I was dividing 423 by 9. I was adding 4 plus 2 plus 3 is 9, and hence this is divisible by 9. 9, or there is no remainder. The remainder is 0, or remainder is 9, whatever you can call it either way. It is divisible by 9. So you are adding the coefficient. So this 423 is 4 into 10 square plus 2 into 10 plus 3. This you are dividing by 10 minus 1, divided by 10 minus 1. So now you can see what we need to do for this. All we need to do is, the remainder here is just add the coefficients. 4 plus 2 plus 3. 9 is the remainder of this division. Yeah. By extending the same logic which we used in numbers decimal system. We started with decimal systems, then we moved to all number systems. Then we moved the same process to algebraic division. Now we all know this is a special case of remainder theorem. Remainder of division of f of x by x minus 1 is nothing but f of 1. In this case, f of 1 is 4 plus 2 plus 3. So now we will be able to prove remainder theorem by the same logic with which we proved that digital root or the digit sum is the remainder of division by 9. The same logic applies in algebra. That is how we get remainder of division of a function by x minus 1, which is f of 1, which is nothing but the remainder theorem. Remainder of division of a function by x minus a is f of a. Now you can, with a little bit of thinking, you can then work backwards and say, okay, how does this apply to x minus a? If it applies to x minus a, does it apply to numbers? We can do that. So if a division of remainder of division of function by x minus 2 is f of 2, then I should be able to use the same rule to find remainder of division by 8 in decimal system, and you can do that. You can then work backwards from algebra to numbers. Again, I think what I'm trying to impress here is the consistency of the approach between numbers and algebra, between number systems and algebra, because numbers, decimal number system abstracted to number systems, abstracted to algebra. That's the interesting part here. So you can then write a extension to the sutra we wrote for multiplication. Now we can say for remainder, all you have to do is cancel x minus 1s or find f of x for remainder. So in like hardly 4 or 5, less than 4 or 5 lines, and not even sentences, these are phrases, you are able to then condense the learning of how to deal with multiplication and remainder of 9 in across number systems and algebra. You can extend the same for division by 9. I mean, just one more application I wanted to show. If I am doing 421 division by 9, here I want the quotient. So one process we do is, I draw one line from the right. This is called the remainder line or decimal line, whatever you want to call it. And I start with the left 4. Then I add 4 plus 2, 6. I add 4 to the next number 6, next digit 6. And then I add again to 1, I get 7. So 7 is my remainder, 46 is my quotient. Or 46.777 if you want to if you need the answer in decimals. So all we are doing is starting with the left, adding the digits to the left digit and writing the next quotient number until we hit the last. The last sum is the remainder. Again, it's very easy to think through why it is working. I'm not going into that now. So if you take a slightly bigger number, 2, 3, 2, 8, 3, 4, 9 divided by 9. This is my remainder line. I start 2, then 8 plus 2, 10, then 10 plus 3, 13, then 13 plus 4, 17, 17 plus 4, 17 plus 9, 26. Now this 26 is greater than 9, so I divide it once again. 2 and 8. 8 is the remainder. Quotient is, now these extra digits I need to pass. So 7 plus 2, 9. This 1 will go here, this becomes 4. This 1 will go here, this becomes 1. This 1 will go here. This is the quotient. This is the remainder. So you take the leftmost digit and keep adding the digits. Be careful to pass the digits appropriately so that we can get the quotient without actually dividing. We're getting the quotient by adding. And the same thing can be then taken to algebraic expressions. For getting the remainder of, let's say, an expression you're dividing by x minus 1 and you want the quotient. So 4, 3, minus 2. So 4, then 4 plus 3, 7. 7 minus 2, 5. So 4x plus 9. 4x plus 7 is the quotient. 5 is the remainder. So again, one more example of how we started off with numbers and use the same process in algebra. And you can also use the same process for quinary, other number systems as well. Again, an example of a division, a method for division, which we start off with decimal system, explore if it is applicable to other number systems, explore if it is applicable to algebra, and it is consistently applied. You can add it to the list of sutras now. For quotient, draw the remainder or decimal line before the last digit and add to the left until you get to the remainder line. It works both for numbers or algebraic expressions. So not only have we covered a lot of ground in terms of 2 or 3 operations, but we are also able to then see that these operations are applied consistently across situations, and also write a set of sutras in our own language, in whatever language we want to make sure that we sort of understand the concept and write whatever is needed for it to be comprehensive yet very concise and easily carried around as a companion for as long as we learn maths. So that's what I had in mind as a small set of examples of why we need to take inspiration from the acharyas who wrote shastras in Sanskrit in India of the past, and while all of that knowledge can be claimed to be subsumed by modern developments of sciences, but my personal view is, for a discerned learner, there is a lot in here to learn, and children, it's a tool to inspire children to take this forward, and who knows, where they will apply it. These concepts are timeless. So that's what I had to share with all of you today. I'm happy to take any questions.
Thank you, Sripathi.
For
Thanks
those
a
of
lot.
you who want to explore this a bit more, there is a YouTube channel Bharat Nyan, where there's a playlist called Ganita Ratna Kosha, where I've put a lot of these techniques in, on the, it's there on the YouTube channel. You could, go and explore them.
Thank you once again, Sripathi. Thanks a lot. So as Sripathi said, we'll be happy to take any questions now. The feedback form, yes, it has been shared in the chat section. It has also been made live on my center. So please fill that in by 9 p.m. today, and you will get the acknowledgement record by email before noon tomorrow. Um, Lakshmi ma'am is asking how to join the course. Yeah, and as Priyanka and you, some of you would have seen in the comments, this was, just of course an hour session, but we are organizing an 8-hour workshop with Sripati in the middle of this month, across 19th, 20th, 26th, and 27th October, I guess. And so while you're filling in the feedback form, you'll get a question on that. That if you're interested to, attend that session, attend the 8-hour workshop, please, enter yes and, register yourselves, and we'll be sending more details to you. And after you type in yes, you'll immediately get an email with the details of the session in terms of what we'll be covering in that session. So yeah, please, do that.
Do you want me to spend a couple of minutes and give an overview what we will cover in that,
Absolutely,
Karthik?
it'll be
Yeah.
great. Absolutely.
So,
Yeah.
so the idea is to take some of the interesting techniques across what is popularly known as Vedic maths, and also textbooks of Bhaskara and Brahmagupta, from the past, like Leelavati, and there is a book by Brahmagupta called Brahmasputa Siddhanta. There is a book by Mahaviracharya called Ganita Sara Sangraha. There are a few of these very well, nicely written texts, and all of them give a multitude of techniques for doing the same operations. I mean, all of them talk about Ganita basically, and a lot of them also talk of astronomy. So I'm not going into the astronomy piece, but if we stick to arithmetic and algebra, the idea is to take some of those medley of those techniques, and which I think are very, very relevant, and also create a set of sutras for all those techniques by the end of the workshop, which you can take
Sure.
away with you.
Sure. Absolutely.
Okay.
I'm fishing for some questions. I think we covered a bunch of them during the session itself. Okay, so Sridevi ma'am has a question, and she's asking, why did we add and subtract and multiply from right, but division is always from the left? Why is that so?
Multiplication and all subtraction also you can do from left, actually. Even subtraction we can do from left to right. Addition also we can do addition, subtraction, multiplication, everything too we can do from left to right. But division we can't do from right to left, right? Because you have to start. It's think about it. If you are dividing 623 by 4 or 5, 600 plus 20 plus 3. So how can you first divide 3 and then go to 20 and then go to 600? You can, but you have to devise a longer method. The method will be longer. So we do from left to right, because it is laghava. It is short. The shortest method of dividing is you can divide as long as you remember place values and you know what the place value system means. You can divide from left to right or middle. You can start anywhere. But the shortest shortcut will always be for division. Will always be from left to right, and that is why it's only taught left to right. But multiplication, I would encourage children to do multiplication also left to right.
And Nalini ma'am had a question on ideas for primary kids to teach addition and subtraction. I think a bunch of these you had covered in your earlier session with us in
Yes.
August. So Nalini ma'am, the video
Complements
is
is a
there on
very,
YouTube.
very nice thing.
Yes.
Yeah. Complements
So
and
ma'am,
subtraction is a very interesting way to
yes.
teach.
Yeah. So ma'am, the video is there on YouTube. So if you search for it, you'll be able to, locate the video, and please watch it at your own pace, and I'm sure that you'll go back with a bunch of concrete ideas. Sumita ma'am is asking for any books on sutras.
So there is one book in the market available called Vedic Maths by Swami Bharatikrishna Tirthaji. So you can read that book if you're interested. And there are translations of Bhaskaracharya's books, Leelavati, Bijaganita. There are translations of Brahmagupta's book. There are of all the Indian acharyas, the books in Sanskrit. There are translations available in archive.org. You can Google their textbooks and you will find translations in English. It will take a little bit of effort to read and digest them, but they are definitely available. They are probably not in a readily digestible form. You need to spend some time with them and to understand what they're saying, but they're definitely available.
I think we've covered most questions, and of course, Ruchi ma'am is saying one more jewel in the crown of CENTA, and Ruchi ma'am had also typed in when you were explaining that you are like the great mathematician Shakuntala Devi. So, and I've
No,
completely,
no.
agree
I
with the
wouldn't say
sentiment.
that, but yeah, but the idea is not about speed. The idea is about the understanding what is happening in arithmetic. That if you ask children, I ask children, what do you think, negative numbers came first or zero came first? You would be surprised. 9 out of 10 children will say zero came first. Was zero invented first or negative number invented first? Similarly, if you ask children to explain why they multiply, whatever we learn in school as multiplication method, you ask a question why. Very few children will tell you any answer which is different from because the teacher told me to multiply like this. The idea is to understand what is happening, so that once children understand, then they will be quick. They will find their shortcuts to make it quicker. But the idea is to help them understand what is happening in the process. That actually gives accuracy first and then speed. That is more important. Blind speed is of no use in my mind. Absolutely useless if you just do it without understanding the process. You understand the process. Because you understand the process, you do it faster. Yes, great.
Sure. Thank you, Ranjana ma'am. Thank you. Thanks a lot. Thanks a lot for the appreciation. Uh, So yeah, I think we've covered most questions. Thanks a lot, Sripathi. Thank you once again for this session, and we'll see you on 19th, 20th, 26th, and 27th. And it's gonna be a marathon, 8-hour long session with Sripathi. So those of you who filled in the feedback form, as I said earlier, in case you're interested, if you like the session, which I'm sure all of you did, please mark yes to attend the workshop, and you'll get an automated email confirming the receipt of your feedback, and also that you are interested in the workshop and what are the details of the workshop. And Sripati already took a couple of minutes and conveyed what we'll be covering in that workshop, so you can in case you missed that, please just rewind back and then watch it. So that's pretty much it from our side for today. Thank you once again for joining us on this wonderful evening. Tomorrow we are going to have another session on apologies for the sound at my place. We are going to have another session tomorrow in which we are going to be exploring how you can effectively start utilizing my center and make it a part of your daily professional daily life, in terms of the quizzes, learning resources, interacting with other teachers, and so forth. So same time, same link, we will also be sharing the link again on email. So do join us at 5 p.m. tomorrow, and we are going to learn by doing stuff tomorrow. So that's it from our side. The feedback form, yes, we've shared that in the chat section. It's also available on my center. Please fill that in by 9 p.m. today, and the acknowledgement records will reach you in your email inbox by 12 noon tomorrow. So yeah, that's pretty much it from our side. Thank you, Sripati. Thanks a lot, and
Thank you. Thank you.
hope all of you have a wonderful evening ahead. Thank you.
Bye bye. Thanks.
Bye.